Okay, welcome back to Advanced Applied Econometrics in the second week now. So we have gone through the statistic reviews, which hopefully will be helpful for the next step in our material. Now in this second week, first of all, I will give you some very quick introduction, the motivation for learning econometrics in our course here. And then we will again look back into the class of general linear models, usually denoted as GLM. And a very famous member of that class is the ordinary least squares, or the OLS, that you hear all the time already, right? Now, so within OLS, we take a look at an example, and then from there we go to the matrix notation of it, which is quite different from what you have seen before. And we will see shortly that it's more convenient to have this sort of matrix notation. And again, look back how is the mechanisms of estimating the OLS and how we can do that with matrix algebra. So to equip you a bit further with matrix algebra. And then finally, we could look at the sampling properties, which linked directly to the sampling distribution part that we did last week in the statistic review now, and how important it is to evaluate our estimator. And so let's go. Okay, like I mentioned last week, relationships between economic variables are at the core of our interest as economists now. So we really want to know what causes what. What is the effect of A on B, how B changes when A changes. For example, I remember during micro class, I mentioned with you about the assumption of profit maximization of firms. Now, assuming this holds in reality, then we might want to see how firms react to an increase in price. Then firms should increase their produced quantity. Then we will not only want to see if that's the case, the sign of the effect is positive, but also we want to see how much, right? Quantify it in using real data. So that's what we really interested in. Another example is, for example, the angle law. Also in micro, we learned that the elasticity for food is based on the empirical observations of earlier economists saying that this elasticity should be smaller than 1, right? So for example, we may want to say, okay, if this holds for our community, and if it's smaller than 1, then how much? Such kind of things. So using econometrics can help in these cases using data and statistical techniques. So there's several ways we can do that. Another way, for example, you set up some mathematical models in some other course. Also this summer term, some of you might have checked out already. And then use simulated data. However, in econometrics, this is typically not what we will do, but we use the data collected from real life situation, what actually happens in the economy, to quantify these relationships. Okay. And this is one important part of empirical analysis. And you see, if you look into the literature, you will see that these techniques appears almost everywhere in every field of economics, energy economics, finance economic, labor economics, land economics, everywhere. And also in agriculture economics. But actually, agriculture economics turned out to be one of the earliest fields of economics where this technique is applied. It's quite interesting. When we come to the t-test, for example, I will tell you the origin of it, and you will see it's directly tied to agriculture economics. Okay. So therefore, it's very relevant for us, and that's why also here in this ethical program in Bonn, we focus on invest a lot of resource in order to make this advanced applied econometrics course helpful for your use later. Nevertheless, if you talk about econometric toolbox as a whole, it can take you years and years and years to learn all the techniques, all the estimations, all the sort of models inside, because it developed quite rapidly now. And a model can go very quickly sophisticated in all aspects now. And if you look, sometimes by now you must encounter some scientific articles, economics literature already, and you can see that it can get very complicated now. Therefore, not only that you're able to apply it to your own analysis, but being able to read, to understand these articles also required certain knowledge of econometrics. But not just scientific articles, actually, what the book I recommended to you, Every Data. If you look on the media, like all kind of articles around, a lot of time it requires some certain knowledge to be aware of there's some problems in there. So that's definitely helpful. Not the only way, but one very helpful way to learn econometrics. We will not be able to cover the entire toolbox in there, because I mean, it takes decades. I myself consider also that I know very little about this toolbox, a very, very small share. Now, however, we will guide you through some main techniques, some framework, so to equip you some basic understanding so that later on, when you need to develop something on your own, you have a firm basic already to walk on your feet now. And that's what we're going to do during this course. Now let's look at some certain types of models, econometric models, based on different types of data. Now, the first one is the time series models. Here when we talk about time series models, it refers to those models that describe the relationship between the present and the past of certain economic variables like price. So sometimes you hear the term auto regression model. So regress one variable and upon its past. However, the use of these models is rather limited and not much involved in economic theories, especially in the field of agriculture economics. In finance, economics is used more often and still can attach some theory in there, but rather limited compared to the use of other type of data that we show as the following. Then we have economic models with time series data. So what's that then? I mean, the difference, it's just here, the way we distinguish is relative now. There's no clear definition over there. So these models describe the relationship between different economic variables over time. How the relationship change, how the relationship of labor force and GDP, for example, relationship of the use of nitrogen and the the yield of potato, how the relationship of farmer awareness and technology progress in agricultural production over time. So you consider these relationships over time. And then we also have cross-section models, which typically focus on the relationship among these economic variables among a pool of population of individuals. Now, individuals here, or you call it units, or you call it observation, just means, for example, the data that's spent over a farmer community within a region, or different field slot, or different markets in the same country, cross countries even, but at one point in time. So one point in time, again, is a relative term. It doesn't necessarily mean that you have to have the data recorded exactly on that date at that time. Now, it may take you even like to collect the survey. When you do a survey over a certain community, it can take you several days or several weeks to collect the data. Now, however, there's good reasons to treat these data units as at the same time, one point in time. And then there's also so-called panel data models, which Professor Hütter will take lead with you in June. So these models explore both the time dimension and the cross-section dimension. So look at the relationship between variables for different individuals and how this relationship among individuals evolves over time. So very complex, but also very informative, efficient way of exploring the relationship. So now within this course, we will only focus on cross-sectional models, panel data mainly. Sometimes we will also look at the models with time series data inside, but not so much. And time series models is something that we don't cover at all in this course. However, as a personal research interest, I work a lot with time series data and also economic models with time series data because directly relevant for commodity price analysis. So whenever you're interested in these models and or you have questions, you're very welcome to initialize a discussion with me. I would be very interested in knowing your idea. Okay, now let's start with a very simple example. Now, we consider an economic models TR equal beta 1 plus beta 2 times B plus beta 3 times A. So you see such kind of models all the time already, either in microeconomics or in your earlier education of econometrics. Such equation appears all the time now, maybe with different notation and variables. And here, the problem we have is the total receipts of a hamburger chain per week that we're interested in estimating or finding the relationship with the price, the average price of the menu items in that week. And the second variable is A, advertising expenditure spent in that week. So we're interested in knowing how effective our advertising activity and pricing activity is in terms of increasing the total receipts. So that's a very simple setup over here. Let's quickly look at the interpretation of the elements in this equation now. So the term regression coefficients, by now you know where they are already, right? So beta 1, the first coefficient, usually called a constant. That is the level of total receipts that you will get if price and advertising set to 0. Well, obviously, because if these two is 0, then you plug in here 0, this term is also 0, and at the end you have total receipt equal beta 1. And then you have beta 2. You know that from micro already, right? That is the slope of the price. If you plot the total receipt against the price, this will be the slope of the line, right? So it's the derivative of the total receipt with respect to price. And by construction, the derivative of the partial derivative of total receipt over price will tell you the change, how total receipts changes in its unit when price increase or decrease or change in general by 1 unit. But remember always, when we talk about partial derivative, meaning we hold other factor, all other factors. Here is only A, right? Because we have 2 explanatory variables. Is held constant. So that is the term ceteris paribus, right? The famous CP. So this is the first mantra that you should remember when learning about OLS interpretation of the coefficient. Ceteris paribus, holding all other factor constant. Now, if you miss this part, probably you will get deducted some point in your assignment of your test, for example. And then similarly, you also have beta 3, which is the slope of the equation with respect to A. Then it tells you how many units of the total receipt will be increased or decreased when the advertisement expense changes by 1 unit or increased by 1 unit. And now we hold P, the price constant, okay? And also this we had, remember in micro already, so the partial derivative with respect to the explanatory variables is called the marginal effect. Now, marginal something is measured by taking the partial derivative, the first derivative, of the interested variables with respect to that explanatory variables. So marginal effect is another name of the regression coefficients in the case of OLS, but only in OLS. We will see that when we see other types of model later in the course. Now, if we try to present this relationship on a 3D map, because now we have 2 variables. So we may also want to present it on a 3D map. So because you have 2 explanatory variables plus the intercept, then this can be viewed as a plane, not just a line of the independent variable against one of the explanatory variables, but a plane, because we consider 2 explanatory variables. So here is where the intercept is, where your regression plane cross the vertical axis or the total recip. That is where when you set all other variables to 0, you will get the resulting TR. And then also the slope in the P direction is this one. Now, so presumably you hold A constant at one place and you kind of flip the plane to the P direction. You will see how the effect is. So it's like that. And of course, when you increase the number of explanatory variables up to 4, 5, in one case, I even had 25 explanatory variables in my regression for the paper, then it's hard to have a graphical illustration of this process. Just that you know. One thing we should keep in mind also this state is just a reminder actually that this regression plan, or even when you talk about a regression lines, they don't cross all the observations that you have in this space, right? It's just the best linear approximation of these observations together, which means in some metrics, in some certain criteria, it's closer, and it describes the best, the relationship, the average relationship among the variables for these observations we will see. Do you already know how least squares estimator works? Well, I guess you may have some impression. If not, then also not a big problem. So least square estimator, as the name suggests, is done by minimizing the sum of squares residuals of the regression equation. So you chose the parameters B1, B2, B3 in order for the regression equation to minimize the total square distance from each observation to the regression line. So that's the idea that we have heard from time to time now. And look, this is actually the solution of that minimization problem. How scary that is. The summation notation, meaning you solve observation by observation and then sum them up at some point. And that is, we only have two explanatory variables, meaning two coefficients or various coefficients, including the intercept, to estimate in this case. Imagine the case, like I said, I have 25 coefficients and thousands of observations. How are you gonna do that? Therefore, in this case, the matrix algebra or matrix notation will save us a lot of space. So the first thing when you see this slide, you may also see that, okay, that does look very strange to you. They may know you, but you may not know them. Same for me 5 years ago. So that is also because I think by the time we learned it earlier in school, we're just too young for knowing what's the application and don't have the motivation to learn it. But now with this, I hope it motivated you a bit already to get familiar with matrix notation and also later with matrix algebra. So the thing is, because it's much shorter, much nicer, and you don't have to take, I don't know, hundreds of pages for your solution. Therefore, it's very popularly used in the textbook. Also in scientific papers, you will see this thing a lot. So once you understand it, you know exactly what's going on. And also for certain, computation software, statistics software, like programming like R, or what I always use, MATLAB, is much nicer to understand this matrix notation and apply it into your own coding. So that's why we learn it now. So with this notation, all your parameter or regression coefficients that you must estimate and you're supposed to estimate collected in letter B. And here, usually when they write it in small bold letter like this, is a vector. Now, so you collect all the parameters, each element, each value in a vector called B. Now, and the big capital letters usually point to a matrix. Now, so there's a matrix X, the transpose of matrix X, like Bram transpose. What transpose means, we will see shortly. Times X. And then the product of this will be inverse to the power of -1 if we talk about scalar or numeric algebras that we used to in microeconomics. Is called to the power of 1, but now it means the inverse. What inverse is, we will also go shortly up to here. And then again times the transpose of the matrix X and times Y. So Y here is a small letters, and then again vector, right? So we will go deeper a bit to understand what it means and why it is the way it is.